So in this video, I just want to overview the basic concept of what circuit analysis is from kind of an academic point of view. And I'm going to try to kind of pose it in terms that you've probably heard in your daily lives before. It's always easier if you can relate new concepts to things that you're already familiar with or intuitive to you. In addition, one thing that I wanted to point out is I'm going to use a lot of terminology that you might not have heard beforehand. Don't worry about it. Just try your best to understand what I'm saying. But if you can't remember every term or if you haven't heard it before, that's totally okay. It's really to be expected. So when you think about circuit analysis from an electrical and computer engineering point of view, which is what that acronym ECE means, the first thing that probably comes to your mind if you're going down that route and you've ever pulled out your program of study is, man, I have to take a lot of classes that have the term circuit in them. Maybe you've seen the term DC circuits course or AC circuits course or electronic circuits course or digital circuits course. And you think about it, it's like if you're taking a different class on all of those, right? There's clearly something different between those classes, but there must be something in common since they're all called circuits. So let's think about what actually makes kind of those separate sub-studies of circuits different. Let's focus on the first two for now, DC and AC circuits. So hopefully just in your daily lives around you, you've heard the acronyms DC and AC before. DC is an acronym for direct current. AC is an acronym for alternating current. And in the context of where you've probably heard those is in how actually the electronic or electrical devices around you are powered. If you have something that's mobile, like maybe your mobile phone, you know that that's actually powered by a battery. And you've probably heard beforehand that the type of electricity that powers those types of devices through a battery is direct current electricity or DC power. In addition, any component that actually plugs into a wall, you've probably heard beforehand that that's AC power or alternating current power. And we'll dig into those a little bit later, but just know for now that one way in which circuits can differ when you're actually going through your academic studies is in the nature of the actual power. And remember, power is nothing more than the rate at which energy is transferred that's actually supplying the circuit. So that's one way you can differentiate types of circuit analysis. In addition, what's the difference between maybe the first two and the third one, DC and AC and electronic? Well, really, what you'll see if you go down the road of ECE is those classes are different in terms of the types of components that are actually involved in the circuit. In DC and AC circuits, you'll predominantly be analyzing circuits that have passive components in them. And passive is just a fancy way to say that these components don't need to be powered in order to work, versus active components need to be powered in order to work. From an electronics point of view, the most simplistic and common kind of active component is an amplifier. We know that energy is conserved. So if I take a weak signal in and I want to make that signal stronger in amplitude, I can't do that for free. There's no free lunch. I will have to actually supply power in order to convert it to increase the amplitude of that signal through amplification. And of course, there's tons of different active devices. At their core, they all are based upon semiconductor technology. When you're talking about analog processing, and hopefully everyone knows that word from the first homework, you're traditionally talking about amplification type applications. When you're talking about digital processing, those semiconductors are being used as digital switches, which are nothing more than transistors. So long story short, when you're talking about electronic circuits, usually those are the first classes that you're dealing with where you're actually analyzing components or devices that operate using semiconductor material. In addition, how do you differentiate? What's the difference between the type of analysis you'll be doing in digital circuits versus the other circuit classes? Well, you all already know this to some extent because we've already dealt with digital circuits. Digital circuits actually process information which is encoded in a discrete form, particularly typically a binary form, a bunch of zeros and ones. So there's lots of different things that can differentiate circuit analysis kind of classes or fields of study, the nature of the power that's being supplied, the type of components, the nature of the information that it's processing. However, even though there's a lot different in the different subsets of circuit analysis, there's a lot of things that are in common. First and foremost, when you think about a circuit, in general, I've used this word source a lot. And source, we're just going to use it as nothing more than the actual source of power that makes this circuit, which we still haven't defined yet, do something interesting. So are we using a DC source to power, or are we using an AC source to actually power? In addition, most circuits, in order to do interesting things, are going to require some sort of information as input. And we're going to call the information as input, which is typically going to be encoded in some type of electrical waveform that varies over time, a signal. So circuits take power in order to do the useful things. They take a signal as input. And typically what happens is they will actually drive something that's known as a load. So one of the examples that I gave when I taught this in person this semester is if you've ever walked around and thought about the way that like an automatic towel dispenser works. So what is the kind of source, the signal information, and the load in that case? So the source is just how it's powered. So by and large, you can assume that if something is sitting in a building like this, that it's actually going to be powered using AC power. So maybe it has an AC power serving source that's actually serving as the source of that circuit. What kind of information is it processing? Well, you want to dispense towels when it senses that a person is in the proximity. So there's some small sensor on the front that has the capability to tell whether or not a person is there. So it's taking the information out of that sensor and it's actually using it to do the interesting thing. And what is the interesting thing in this case? Well, you actually want to dispense paper towels. You're going to need to use some sort of motor in order to make that work. So in that case, the load, or the thing that's actually taking the power, condition on the information to do the interesting thing, is the actual motor that's driving the towel dispenser in that case. So we're going to call a circuit anything that takes some type of closed loop interconnection of components, or just things, and we're going to define some things in this class that can be interconnected, that's going to take power in the form from some electrical source, that's going to use that electrical power to drive some load, and it might take in some information in order to determine what interesting function it does. Like for the case of the automatic paper towel dispenser, I could just have that AC source continuously dispensing paper towels, but in the absence of an information source, that's not going to be a very useful real device. So let's talk about like some practical circuits in electrical and computer engineering. So what I'm going to do is just ask you to identify the sources, the loads, and the actual components and the sources of information within each of these very common devices that we don't encounter on a daily basis. I guess maybe depending on what kind of car you drive, you might deal with these types of systems very frequently, but definitely the first one, the audio receiver. And let's also ask if we can call these electrical systems and if the difference really matters. So how does an audio receiver actually work? Think about clearly the audio that I'm speaking right now is going to be captured and delivered to you down the road via YouTube. So what's going on? Well, I'm actually speaking and I'm generating acoustic energy in the form of an acoustic wave that's propagating in space. It's going out and it's exciting the microphone. And what is the microphone actually doing? Well, it's an example of a transducer. It takes acoustic energy on the input and actually produces an electrical signal on the output, which corresponds or encodes the information inside my voice. However, that information, it's not going to be very useful when it comes out of the microphone. It's going to need to be conditioned in order to translate into a useful form. Maybe I will need to filter out other sources of information in that signal that I don't want if I'm trying to process only my voice. Maybe there's some background noise that I want to get rid of, or maybe there's just noise associated with the actual thermal behavior of the actual components. In that case, you would call that white noise. Maybe I want to do some processing to clean up my signal a bit, and maybe I need to amplify it as well before I actually even worry about this concept of digitization. And that kind of processing where you clean up a signal and amplify it is often known as signal conditioning. So that's going to involve things like filters and amplifiers, and hopefully those are some terms that you've heard before. And then if I actually want to post this online, that way you can watch it whenever you want, I'm going to need to somehow make it in a form that's compatible with computers. And that process is known as digitization. And I think we talked about beforehand, the process of going from an analog signal to a digital signal is done through a component known as an analog to digital converter. And the way that once I have the signal into a bunch of ones and zeros, I might use some sort of mini computer, which is typically known as a microprocessor, in order to do some additional things, whatever I might want to do on the audio receiver. In this case, just store it. Eventually going to send it and upload it to a web server like YouTube in order that you can watch it later. What about a radar transceiver? Anyone ever heard of the term radar beforehand? I think most of you have. What it means is radio detection and ranging. And the way that those systems work is they take some type of radio frequency signal and they actually transmit it out on an antenna. And then that signal, as it's propagating in space, will reflect off of all of the objects that are around it. And hopefully, if we take and we capture that reflected signal using an antenna, we'll have the capability to kind of say interesting things about the environment around us. Maybe how far away an object is, what type of object it is, and so on. So you can kind of think of the different information sources and the power sources. How am I ever going to get this small signal to propagate a long way in space? I'm going to need to amplify it. When I get that reflection, how am I ever going to take this very small and noisy reflection and gather information out of it? I'm going to need to condition that as well. So long story short, there are tons of practical circuits in electrical and computer engineering that really make all of the interesting things in our life work. But when someone's actually talking about classical circuit analysis, what are they talking about? Well, in classical circuit analysis, you're talking about making all of the components, everything that you deal with in the world around you, modeling it using a finite small set of components. And as an example of this, the first thing that we're going to talk about as a component for our circuits is the idea of a resistor. So if you look up here on the right, hopefully everyone recognizes in the upper right, that's just a heating element that you have on your stove. So you know if you have an electric stove that it's plugged in to the actual AC power source in your house, and somehow it's actually generating heat. And that's actually what it's doing. It's just converting that electrical energy that's produced however CPS actually produces your power into heat in order to achieve a useful function like cooking food. So if you look at these components in the upper left or the bottom, these are actually the same thing. They're just different form factors. These are actual resistors. This is known as a through-hole resistor, and this is known as a surface mount resistor. And resistors are devices that are intended to limit the flow of current. However, the way that they do that is actually to just cause all of the charge carriers to kind of collide into one another. And that collision actually causes the electrical energy that's pushing the current through the component to turn into heat. So even though all three of these things, they do totally different things, and they certainly look totally different in form factor, we can model all of them by a component which has a known relationship between current and voltage, which we'll talk about a little bit later, but that basically does nothing but describe how electrical energy can be converted to heat. And that's the way that classical circuit analysis works, is you try to take the entire world around you where everything just looks dramatically differently and everything is intended to achieve all these different functions. And you say that from an electrical point of view, I can describe a relationship between its key electrical quantities, namely its voltage and current. And if I can write a mathematical equation that models how it behaves, then I can model it, even though it looks in this weird, it may look in a ton of different form factors, it might try to achieve a ton of different objectives, I can model it using a common language. So in that case, we talked about it's a resistor can be used to model anything that actually turns electricity into heat. Maybe if you're watching this on a laptop and you can actually pull out, if you have your charger plugged in, you can actually hold it in your hand and feel how it's getting warm. So I can model the electrical behavior of this using some sort of resistor. And I have a mathematical equation that describes the relationship between the fundamental electrical quantities, and that's known as Ohm's law. And we'll talk about that a little bit later. So just note that when you're talking about classical circuit analysis, you're going to take things from the real world and you're going to try to fit them to a subset of these fundamental component models, and you'll describe everything like that. So that's all I wanted to say for the first video. I realize this is probably a very, very confusing video, especially in an introduction to general engineering, but hopefully you got some key material out of that, namely circuit analysis is really a broad field of study. You can talk about kind of the practical applications that we gave you a couple examples of through the audio receiver and the radar receiver. But from an academic point of view, especially what we're going to be doing initially, because we're only going to delve into DC circuits, is look at how we can work with these fundamental models of passive components, which are excited by DC power, and describe the relationship between the voltage and current in each.